But of course
It is more directional.
it's more critical as well in the way you align it.
It becomes
More difficult to get it aligned properly. It's very directional. What we've said so far in my examples are to do with transmitting antennas. But of course, whatever you say about a transmitting antenna, you can also say about a receiving antenna. For instance, let's say I have a receiver here with an omnidirectional antenna, and I want to receive a signal from a transmitter over here. Okay. Okay. And let's say I'm receiving 1 microwatt of power in my receiver. It doesn't matter what this is for the moment, but that's the power in my receiver. And this is an omnidirectional antenna. So it's a dipole, let's say. Now I'm talking about the receiver now. Now what do you think would happen if, instead of using this dipole, I put here, I connected it to a Yagi?
Dipole. We receive
Receiver.
more than 1 microwatt.
Yes, we would expect to get more than 1 microwatt in our receiver. Because what I'm doing, right, I am concentrating my receiving energy, all right, in this direction.
But when we use that takes the dipole also, antenna, for that transmitter. We use dipole.
Well, at the moment I've not said what we've used here. It could be anything.
If you use dipole,
Yes.
the power will be the same or different.
Well, obviously, if I change the type of antenna I use here, I will also change the power here. For instance, if I make this more directional, then I'll increase the power here,
Yes.
make it less directional, less power. But I can also talk about the gain of a receiving antenna, just the same as a transmitting antenna. By making the receiving antenna directional, again you can talk about the gain of the antenna. Just exactly the same as you can with the transmitting antenna. Talk about a certain gain. More or less, whatever we say about transmitting antennas applies equally to receiving antennas, usually. A good transmitting antenna will make a good receiving antenna. A bad transmitting antenna, a bad receiving antenna. However, you probably all know, for example, in TV reception, you don't necessarily have to have a very good Yagi aerial antenna to receive a TV signal. Sometimes just a piece of wire stuck in the back will give you some sort of signal. But of course it's not a very good antenna.
We use the 2 antennas.
2 antennas? You mean to switch between them, or?
No. This one. Sometimes using the V chip and U chip 2 antennas.
Yeah, but only one at a time will be used actually, depending on whether you're using VHF or UHF. You can't, you know, it depends whether you're receiving a VHF signal or a UHF signal as to which antenna is actually being used the most.
Also, we can use 2 antenna intakes.
For what reason? I don't know what you mean by 2 antennas. Do you mean?
Not 1 antenna, 2 antenna.
Well, you've got to be a little bit careful, obviously. You're talking about 2 elements of 1 antenna, I think you're talking about, 2 active elements. For instance, if I have a stacked array, remember our stacked array? How many antennas is that? How many antennas is that? No, it's 1. It's a 3-element single antenna. Don't get confused. If you connect each of these dipoles to the same transmitter, it becomes 1 antenna.
It's not maybe multi-coupler or multiplexer or something, 2 antenna, but it's combined.
Then it's 1 antenna.
I mean, two directional antenna. This way and this way.
Yes.
Connect to 1TX.
Then it's a single antenna with two active elements. That's how you view that. If they both connect to the same transmitter, then they are both the same. They form the same antenna.
One different antenna.
Doesn't matter. They have the same antenna, but it's a complex design. That's all.
You're
Yes.
saying when you make the gain for the antenna TX high, we decrease the power of it. Make power less.
No, you don't make the power less.
Reduce the dipole from the
You
signal.
can make the power less for the same signal at the receiver.
Yeah.
That's what I'm saying. By increasing the gain of the antenna, you do not change the power of the transmitter. The power of the transmitter can be anything you want. What you're doing by increasing the gain is making the strength of the received signal bigger.
Strength.
The received signal. Remember, it's the ratio of strength, signal strength at the receiver.
Doesn't affect the power when they increase the antenna gain?
It doesn't affect the power of the transmitter.
Yes.
No. But if you wanted the same received strength, you can reduce the power of the transmitter if you wish.
Say, but when you increase the antenna gain from TX, the transmitter, I will increase the power for the receiver?
Yeah, at the receiver is where that's where this change has taken place, at the receiver. Now, if you want the strength of the receiver to be the same, then you can reduce the power of the transmitter for a higher gain antenna. To answer your question about different antennas,
No, he was he wants to transmit at the same time to two places in any direction, but in two directions. So one direction is that way and one direction is that way. He wants to use a Yagi antenna to transmit. So
yeah, but the important thing is, yeah,
the same transmitter and they cannot transmit at the same time.
same transmitter.
Yeah.
Then the easiest way to look at that, if it's what you're going to do, you're talking about, like, say, two Yagis in different directions, aren't they? One there and one over here. Is that the sort of thing? The easiest way to do that, if you're connecting them both to the same transmitter, is to think of them together, and you'll get a polar diagram something like this. That's the easiest way to look at it.
Not losing power.
Well, yeah, compared to using one, right, the antenna gain of both of them is less. If you use just one and transmit just in the one direction, you might get an antenna gain of, say, I don't know, let's say 15 dBs. Okay? But if you use two of them, same transmitter, same power, think about it, it's half power going to each one, isn't it?
Yes.
So you've immediately reduced the antenna gain by 3 dBs, immediately. Because you cannot get the same power from each antenna if you've just got the same power in the transmitter. It's got to now divide it between two, hasn't it? That's basically it. You get nothing for nothing. I mean, you know, you're just using the signal strength in a different way, power in a different way.
Variable case, I mentioned that 0 dB, if you like to transmit 100. If you're decreasing, to 50, 100 will be 50, so that we can use antenna with 3 dB.
What we're saying is that would give you the same signal strength in the receiver if you use 50 watts with a 3 dB antenna, yes.
But now this calculation is a little bit different than what we mentioned last week. We said in speaker. We said if we like to purchase speaker by 100
Ah, well, with the speaker, I didn't talk about anything to do with the gain of the speaker.
dB, 3 dB.
That wasn't gain, that was power of the amplifier.
3 dB or...
When I say the power of the speaker, I mean the amplifier, the speaker, the whole thing.
I mean, this is 50 watt and this is 100 watts. So
Yeah. The same thing applies. I mean, it doesn't matter what your system. If you double the power of your transmitter, right? Double the power of the transmitter, forget about what type of antenna you use, what will happen to the power in the receiver? Double. Double.
3 dB.
Yeah, 3 dB, exactly. 3 dB change in the transmitter, you'll get 3 dB change. But what I'm saying is, when we talk about the gain of an antenna, you can achieve the same thing keep the transmitter power the same and double the gain of your antenna. That will also double the power in your receiver.
And the range, it will be different? No.
The range is a different calculation. Signal to noise ratio might change, but range no.
The coverage, it will be...
Coverage depends on what frequencies you use, whether you use VHF,
not
UHF.
dealing with these things.
Well, it does affect it, yes. I mean, you know, obviously the higher the power, the better the chance. As long as the idea is to keep your signal above the noise level, isn't it? Now, obviously, if you're going to try and communicate with the mobile station through buildings, then as your signal passes through those buildings, they're going to be reduced quite considerably in power, aren't they? Particularly at UHF. So if you still want to communicate, you want to make sure you've got sufficient power. But the biggest difference is going to be if you could change from VHF to from UHF to VHF. That will be your biggest change. That will be more beneficial to you than any change in power.
Now, one GSM radio, like, the market, it is Alcatel. You know, they have 3 watt instead 1 point for the regular one. And they said this is better because maybe the
Well, it'll probably give you a better signal to know. What's the radio used for?
GSM.
Oh, you're talking about cellular.
Cellular. They have, you know, now 3 watt.
3 watt. What was the standard? Is it
1.5
1.5.
for all.
So there's a 3 dB increase in power.
3 dB increase, but it is dangerous to the viewer.
Yes, 3 dB more interference on the brain.
Maybe you would like to overcome, you know, that and the passing the building or something. Waves.
It's not always an advantage to increase the power like that. Well, I mean, apart from being dangerous. For instance, I explained, let me just go back, when you talk about radio communication, it can get quite complex. We spoke briefly about tropospheric scatter. I wasn't going to actually mention it. It's only Khalid who came up with his figures, so I had to mention it. But I'll ask a question. Is stratospheric scatter an advantage or a disadvantage?
Either ways.
Yeah, it can be an advantage, but it can also be a big disadvantage. We found in our trunking system at the airport, we're getting interference from Yambo. Now that's a big disadvantage. We don't, I mean, Yambo's a long way away. We don't, and we're talking about local mobile communications here.
Any signal can affect it.
If you get long distance communication, it's not always an advantage. Sometimes you don't want it. You want it just to be local. You don't want that stratospheric scatter.
Ask in the airport if they don't use HF. High frequency, they don't use it, yeah.
No, it's only in Jeddah. Jeddah is the only place that uses
I asked
HF.
how you connect the plane with the far distance. They said by Jeddah. You don't have
Yeah,
HF.
through Jeddah. It has to be through Jeddah. Jeddah is the only place which has the HF communications. Yes, that's right. Has to be done through here. Because it's quite a big, expensive,
Yes,
you know, setup with the power of the transmitters and the antennas and everything.
What is the value of dB that can affect human being?
I really don't know about that. You mean, are you talking about a GSM phone?
Yes.
There's even some argument as to whether it does affect you. You know, they're still doing tests on this to see whether it does affect you or not. And if it does, how it affects. Whether it just gives you a headache or whether it has a long-term effect, nobody knows yet.
Because they said in British, they don't talk more than 1 minute. The mobile, they say. Or 10 minutes. I think.
Is it?
Yes.
What they say?
He
Over
is.
here,
Yeah, they say yes.
if you put 2 antennas, you immediately decrease the dBs by just 3.
Well, I'm just taking 2 identical antennas, say, and you've got a transmitter.
Why is it 3 dB?
Yeah, what I'm saying is this. Let's say we have...
It's supposed to be the half. If it's 15, so it's going to be...
Yeah. Let's say we just take one antenna. Whenever you talk about aerial or antenna gain, don't think so much of the power out here. Think about your receiver and how it's affecting the receiver. Here I have a receiver here. I have a transmitter connected to one antenna. I'm going to get a certain signal strength, say 1 microwatt. Doesn't matter what it is. Right? Now, I then connect another antenna, assume I connect it properly, matched and everything, to the same transmitter, Same power from the transmitter. Okay. Now, it should be clear that that power has now got to be divided between two antennas. So you would expect the power from this antenna
Yes.
to be less by about a half, because half the power goes here, half the power goes there. That's a 3 dB change. So, if we look at these two antennas together, the radiation pattern in this direction has been reduced by 3 dBs.
Make an example that the power may be 10 dB.
Power,
10 dB when I have one antenna.
you mean the gain?
Again, 10 dB. When I
Oh,
have one
okay,
antenna.
right.
When you put two antennas,
It can be reduced by 3 dBs.
3 dB, not 5. Will be, this
No,
will be 7.
this will be reduced by 3 dBs.
Yeah, and the other one also reduced by.
That will be the same. That will be the same, or should be the same. In other words, 7 dBs
And 7 dB.
and 7 dBs, yes. But you cannot just add those two together and say it's 14 dB gain. It's 7 dBs in particular directions.
Yeah.
You know, you can give all sorts of examples like this. I could ask the question the other way around. I have an antenna system which radiates in two directions. And the gain of the antenna in this direction is 7 dBs.
What's the
And the gain in this is 7 dBs. Now if I cut out this antenna and put all the power into here,
10
this will go up to 10 dBs. The reason why it doesn't go up to 14 is because all I'm doing is doubling the power, that's all.
So that if you increase the antenna and the power and
Yeah.
the dBs, the antenna needs to make it more sensitive to pick up the signal.
Basically, yes, when you're talking about antenna, you're talking about antenna gain now. Think about your receiver power. How's any change here going to affect this? That's what you've got to do. That's how you've got to think about it.
The best RX antenna. If you go to the more dB, means more gain, so it's more sensitive to pick up.
That's right, yes. Sensitivity to pick up that signal. We talked about distance this morning, remember?
If you, the receiver is nearest to the X.
Oh yes, of course. That's true. I mean, the distance away that the receiver is from the antenna doesn't matter what type of antenna and what the antenna gain is. The further away you are, the weaker the signal is going to be. But that applies no matter what type of antenna.
So that the effective now of the communication transmitting, it is the distance, the gain of antenna.
The gain of the antenna, the power of your transmitter, the sensitivity of your receiver.
The weather, based on the rain, and
Yes, anything in between, any objects in between the transmitter and receiver. So many things can affect what sort of signal, your communication.
What is this distance between two antenna with two receiver? Avoid the interference.
To avoid the interference.
Yeah.
How do you mean by that? Do you mean,
I use two RX and two frequencies different.
let me just try and draw what you're saying here. You're saying you use one transmitter.
No, two RX.
Wait a minute. What are you trying to receive? From what?
I need the distance between two antenna. With two antenna and two RX.
You're talking about just designing a receiver now.
Yeah, receiver.
Okay, so you've got a receiver number one, another receiver over here, two antennas connected to the receivers.
Avoid the interference between two RX. Distance between two antenna.
different frequency. Is it the same frequency?
I'm not quite sure what you're trying to do here. Are you trying to receive one signal from a transmitter?
No, different frequency.
Different frequencies.
Yeah.
So they're both tuned to different channels.
Yeah.
Well, that's not going to do anything. There's no connection then between these two. Is that what you're trying to say?
Sorry.
Looks like. But
Is this a practical case, or is it just something you thought about as in theory?
the practical what we have, it is one antenna,
Yes.
16 other receiving signal, and the tuning, it is, the selective tuner. It is now it is the maintained these things.
Are you saying you got one antenna
One antenna
and there's 16 different receivers,
Yeah.
each tuned to a different frequency?
Yes, it doesn't matter. Only one antenna is in it.
No, two transceiver. Two transceiver.
TX,
Two transceiver.
Uh-huh.
It will be interference to.
I don't know. It depends on the frequencies. Depends on the frequencies. See, now at the airport, when we talk about HF communications, you'll notice that your receiving antennas are a few kilometers away from your transmitting antennas, aren't they? This is HF communication now, HF communication. The reason being that your transmitting antennas are very powerful, and if they were very close to your receiving antennas, they would overload the receiving antenna, overload the receivers, I should say.
What does the chip need high power to?
Doesn't need high power.
By the specification?
Probably just to improve the signal-to-noise ratio at the receiving end, probably, yes. I mentioned, I think last week, that they use 10 kilowatts, maximum power.
That one for transmitter.
This is for HF.
Yes.
Now remember, HF is nothing to do with line of sight. We're talking about using the ionosphere there. So it is a different system altogether.
The tracking system what we have in the airports, I'm talking about the linear array.
Right.
We transmit 4 signals with same antenna, one antenna, so that we have 16 channel with 4 collinear array.
It doesn't matter about how many you have here. That's nothing to do with the number of frequencies you transmit on.
I mean, is it, if we transmit, looks like 3 channels transmitting in the same time,
Yes,
different frequency,
yes.
it is not affecting each other? If transmitting
No, it depends on that's to do with what they call the bandwidth of the antenna. Now, when we do tuned circuits, I'm going to cover tuned circuits later, inductor capacitance tuned circuits, reactance and things like that, we can talk about bandwidth. And it depends on the bandwidth of the antenna. An antenna is designed to operate over certain frequencies.
Yes.
Not just at one frequency, it's a band of frequencies. So we talk about bandwidth. And providing the channels that you're transmitting on fall within the bandwidth of the antenna, no problem, it's treated as one signal.
Yes,
Does that answer your question?
yes. So that they transmit the complete band.
That's right.
Band pass filter.
Well, it is like a bandpass filter in a sense, yes,
But it
the
doesn't
antenna.
matter to.
You see, an antenna will be designed to radiate most efficiently at a certain range of frequencies. You can get VHF antennas, UHF antennas, microwave antennas, and they'll be designed to operate over a certain band of frequencies. And providing your transmitter channels fall within that band, it will work.
We'll see what is there.
Basically means if we want to transmit like a signal on 10 mega and a different signal on 30 mega.
Oh, that would be, yes, you would need a very wide band antenna then. And the wide band antenna that they use for that is the log periodic.
Frequencies with different signals. It's not channels in one it's not a number of channels under one band.
No, we have in the airport.
Yeah, but in the airport, in that example you chose HF as an example.
Yeah.
And we do actually do that, but we use a log periodic antenna, which looks a little bit like a Yagi when I draw it on the board here, but in fact each one of these elements are active elements, and basically, very basically, you can say each one of these elements is tuned to a different frequency within the HF band.
How to make it active, all of these?
Just connect them all to the transmitter.
So that
Yeah, actually, the transmitter comes up on a cable, goes to the first dipole, and then actually goes to the next one crossed over, and so on. That's how it's actually done.
so that if they were coming to which element? Going to which element?
They go into all elements.
One element, it is the one who's used in here.
Yeah, basically, if you're, say, operating at the lower HF frequency, you're going to get more radiation from here and less radiation from there. If you change to a different frequency using the same antenna,
At the same time.
Oh, well, let's do it at a different time first. Then you would use more at this end of the antenna. Now if you do it at the same time, both of them are transmitted together. I'm not sure if they do use them at the same time in that case, but they can do. I don't see any reason why not. You've got to be a little bit careful not to overload. You can overload antennas with high power, particularly when you talk about 10 kilowatts. I'm not sure if they do that at the same time. But basically, different parts of the antenna are used for different frequencies within the range. But this, remember, this is a very, very special case of HF communication. And the reason why we need such a wide range of frequencies is because of the ionosphere changing between daytime and nighttime. That's the whole reason for that. This would not be the case if we were using UHF and PHF.
What is called this one?
This is called a log periodic antenna. Log periodic.
What about these, the wires? Different shape. We found also, we have one in the airport, but not this one.
If you look at the antennas at the airport, the log periodics are big long things. Actually, the elements go that way, they're horizontally polarized. And they're mounted on a large mast, aren't they?
Yes.
Which some people can climb. Did you climb it? No?
This one, this man.
Who's the climber? Okay. Anyway, you also find that you've got, I'm not sure if this is what you're talking about the struts holding the mast up?
No, this is the holder the mast. But we have another type with many wires connected, looks like different shape. It is HF.
وصلت الحين ما
You can make an HF antenna through using a single cable.
It's like a grid type if you're using. You know the spider
Something like that.
It looks something like that.
Okay.
Sometimes you
Could
can-
be an HF antenna, the
funny
description.
type.
Yes. I'm not very familiar with it, but it sounds
I
like
think
it.
there is one like that in the US embassy.
Oh, maybe. Yes.
I went there.
Also, there's one like this I've noticed in the US Embassy.
Yeah, they've got
This type as well that they can rotate, because this is directional as well to a certain extent. They rotate it towards the... The idea is they can rotate it towards the country they're transmitting to.
Why did they put it like this?
It could be just convenience. It could just be the mechanical arrangement of it. Maybe it rests better like that.
This way, is it omnidirectional?
No, that is directional towards one direction, actually.
This is the log periodic.
It's the log periodic. It is a directional antenna, it is, yeah.
It's supposed to be omnidirectional because you're using every one of these.
Not necessarily. What we're doing here, remember, the idea is, on HF communication, you use the ionosphere, isn't it?
Yeah.
And the idea is to get reflection from the ionosphere. But really, you don't want to waste energy in the other direction. You know precisely the location of where you want to communicate to. This could be London or New York or any of the other stations where we could have aircraft. Yeah, you know roughly the direction. You don't want to waste energy in the other direction. So yeah, a directional antenna will work, even though it's using the ionosphere to do that.
But each element is dipole.
Yes, it's like a dipole.
Dipole is omnidirectional.
Yeah, but not together it isn't. A dipole is omnidirectional when it's by itself. But you put two dipoles close to one another, just like your stacked array. There will be interference between them to make it directional. Again,
The Yagi is
now a Yagi uses one dipole
one dipole.
and what they call directors. They're passive.
And then they're only to direct.
That's right, they're not connected. Exactly. The passive elements are just there to receive the signal and retransmit it like a little reflector.
Yes.
Only it's directing. You can get passive elements at the back of the of the antenna as well, or at the back of the dipole, which are reflectors. Whether they're directors or reflectors depends on their distance away from the dipole and the wavelength of the frequencies you're using. That's what it affects it. But yes, a Yagi uses a single dipole and a number of directors, maybe a reflector.
So in any antenna, if you use more than one dipole, you are directing the wave.
Yes, what you're saying is in any antenna, if you're using more than one dipole as part of that antenna, it's directional, and it's going to have a gain greater than one,
Either active
or greater than zero.
either active or passive. In this case, it is passive.
Yes, even active. Now that brings another question. Say you have a dipole, which is supposed to be omnidirectional, okay? We'll have a break in a minute. Let me just mention that.
The second line only, we are right.
Yes, I can see some of you are more interested in than others. I don't know. We're supposed to have a meeting this week about you guys.
That's why we ignore the antenna.
Hey, don't ignore it. You don't know where you're going yet. Say I have a dipole mounted at the side of a large mast. Now this mast is made of metal, and so therefore the mast itself can behave a little bit like a passive element.
So that the direction.
Yeah, so although we talk about dipoles, and I've come out with all this fancy theory, in practice, if I have a dipole at the side of a mast like that, and I want that to be omnidirectional, in practice it probably is not going to be fully omnidirectional.
Yes.
Because of this mast acting as a little bit like a director or reflector, depending on the distance, I might actually find, if I was to take the polar diagram of that, instead of getting it nice and circular, I might end up something like this. Right, not quite circular. It's still not too bad in this direction, but you know, it does affect it.
The top of the mast
Yes, if it was right at the top, it would be better, wouldn't it? Same with a car, you know, strictly speaking, on a car, you're supposed to put the antenna right on the roof, but, you know, for practical reasons, they usually put it at the side here, don't they?
The polar diagram, it is opposite, I think, because the passive, it is in the other
Well, that depends on how this distance is.
This is,
Yeah, this distance is critical. That can either be a reflector or director. Yeah, so I'm not going to say which way it is. That depends. All I'm saying is it's not going to be quite omnidirectional because of the mast. Same with a car. Strictly speaking, you're supposed to put your antenna on the roof, but it's more convenient to put it at the either, you know, usually on the boot, isn't it, on the back of the car. So you're going to get a little bit of reflection from the rest of the car.
What if it's
At an angle.
yes, an angle. Just,
Yes, I've seen antennas like that.
most of the cars now have this.
Are they for cellular repeated cellular?
No, radio. And they are at the top of the.
Oh, light coming out.
From the side of the glass. From glass.
Yeah, coming out at an angle.
This is for a cellular telephone. This is for cellular.
Is that for cellular? Is it?
Yeah.
But
This one is when you.
as I say, there are so many different types. Like all we're doing is concentrating on basically what we need to know about, even for us radio guys in Saudi. And you know about a dipole, you know what an omnidirectional antenna is. A stacked array or collinear array would be used for mobile communications where we're not needing to transmit up or down. A Yagi could be used, but it would have to be point to point. And then, of course, finally, microwave systems, we would use a dish. We also spoke last week about the satellite communications. Now, we don't use satellite communications directly in the company for our communications, but of course you should all know how a satellite communication system works. two types of satellite we mentioned,
Geo,
geostationary and low orbit. Now, if you read a book in more detail on satellite, they'll go into other different layers of satellite and tell you there's a bit of a difference here, there. I only split it into two basic parts. The geostationary, because that is where the satellite is fixed in relation to the ground. Ideal for broadcast systems, TV, backbone communications for internet, anything like that, where backbone, the backbone communication system. Ideal for that sort of thing where we're not needing a quick response. The big disadvantage with geostationary was the time, isn't it?
Very expensive.
The delay, yes. Remember the time delay on telephone calls. So it really is not suitable for telephone calls. We, however, can use lower level satellites for that, low orbit satellites, which just are a few 100 kilometers or 1,000 kilometers above the ground. And they would be used, could be used for any type of communication. They, of course, are moving continuously with respect to ground, unlike the geostationary. So special antennas have to be used, sensitive receivers, because you couldn't use a directional antenna for low orbit satellite. At least not directional in a pointing sense. You can say an antenna that will receive anything from the sky could be used for low orbit satellite communication.
Any dipole. It is not a dish.
It wouldn't be a dish, that's right, or at least not a highly focused dish, that's true. Some antennas, there are some antennas for low orbit satellites which use like a mat. And there's a central element in it, and they point to the sky, but they're not so much a narrow beam, they're taking the whole of the sky into, you know, as their scope for their receiving antennas.
What kind of antenna we use for the receiver?
For
HF.
HF, actually it's interesting, HF, obviously a log periodic it makes a good HF antenna because it makes a good transmitter antenna, but with HF communications, remember your wavelengths are quite long. Your frequencies between 3 meg and 30 meg. Now this means long antennas. So on receivers we can get away with something shorter than that. For instance, the HF receiver on a plane, on an aircraft, is much less than the theoretical. There's no problem with this. If an antenna is less than the length that it should be for receiving, it just means you're not receiving the maximum possible strength of signal in your antenna. But generally speaking, this isn't a problem, providing your antenna is tuned to the right frequency and you don't have a lot of interference, then that's not a big problem. In fact, any conductor suitably placed can be used as a receiver antenna for HF. It's not a big problem. And when we talk a little more about, later in the course, we're going to talk about tune circuits. It'll add a little bit more information to us on how antennas work. So there are different types, as I say, many different types of antenna, but one thing we must remember, if it's a directional antenna, it must have an antenna gain greater than 0, mustn't it?
Yes.
And the more directional it is, the higher must be the gain of the antenna. As simple as that. Have a high gain. Okay. I'm just trying to think I haven't missed anything out on that. Yes, okay. Now let's talk. Let's come to a little bit of theory here now, and we're going to talk about tuned circuits. Now, I purposely didn't cover this when we did electronics. I wanted to cover it when I could talk about some practical ways of using it, and not just pure theory. And now we can see in this section, when we're talking about radio, we can see how we can perhaps use tuned circuits. So first of all, let's find out what they are, how they work, etc. We're going back now to talking about resistors, capacitors and inductors. All right. If I have an alternating supply and I connect that across a resistor, I can draw a diagram showing the current through the resistor and the voltage across it. For instance, the voltage across it I can represent as a sine wave. Do you agree with that? An alternating voltage, an alternating sine wave. And I can show the current, so this is voltage, and I can show the current through it also as a sine wave. And notice here, the bigger the voltage, the bigger the current. So resistor circuit, bigger the voltage, bigger the current. Directly proportional. If the voltage is 0 at an instant in time, the current is 0. Voltage in one direction, the current's in that direction. That's exactly what happens through our resistor. Very simple. You can actually draw, you can represent these two waves as a phasor diagram, where you can draw two lines representing, one representing the voltage and another one representing the current. Actually, that would be current, this would be voltage. Let's say this is voltage and this is current. So you could represent them like that. Notice they're in phase. Voltage increases, current increases. You can represent frequency by the speed of rotation of your phasor. But whatever the frequency is, we can show the current and voltage are in phase in the case of a resistive circuit. Now let's have a look at a different component. Have a look at a capacitor. In a capacitive circuit, again, we have an alternating voltage, and I can show that. This is V. But what can we say about the current through the capacitive circuit? Yes?
Voltage leads the current.
No, in a capacitive circuit. Yes, that's right.
Current.
Yes, you can remember it by using Civil, can't you? Did you ever learn this?
Yes.
In a capacitive circuit, current leads voltage. In an inductive circuit, voltage comes before current. So we could show this, if you wish, like that. So this would be the current waveform for a capacitive circuit. The reason why the current and voltage is out of phase is to do with the fact that the capacitor is charging and discharging. That's what's actually happening. And the current is a measure of that charge and discharge. And we can show this on a polar diagram again, or on a phasor diagram, let's say. Let's say voltage is here. And we always assume these diagrams are rotating in an anti-clockwise direction whenever we do these phasor diagrams, by convention. So our current is in ahead of a voltage by 90 degrees. Do you follow that?
Yes.
This is a bit of revision now. You should have been through this before, so it's just a matter of refreshing your memory as to what's happening in the circuit. And then finally, take our last example here, where we have a circuit with just inductance in it. So this is R, this is C, this is L. Okay, now here again we can draw waveforms. We begin with the voltage, let's say, one cycle of voltage. But now, if we use our little memory device here, we see that the current is behind the voltage by 90 degrees. The voltage is leading the current, isn't it? Okay, so the current is lagging on the voltage by 90 degrees. I can draw it something like this. This is the current. This is where time starts here and goes towards here. Again, it's better to draw this on a phasor to see what's happening. There's our voltage. And this time the current is here. This is current. And this is where the 90 degrees is between the voltage and the current. Okay? So that part of it, anyway, we should already be familiar with. The only time it gets a little bit complex here, and in fact the only time we really need to talk about phase and things like that, is when we start to mix these three components. When we start to have circuits with resistors and capacitors, or resistors and inductors, or capacitors and inductors, that's when we start to have to think about these phase angles. Do you follow that? I'm going to draw a circuit here as an example, showing a resistor and a capacitor. I'm drawing the old resistor symbol, but of course it doesn't really matter. This is input. This is output. Now, does anybody recognize this circuit? It's a type of filter, isn't it? It's a low-pass filter. So we're going back to our low-pass filter, but now I'm going to talk a little bit about the math that's involved here. Okay, only a simple example, but let's have a look at it. If I wanted to compare the input with the output of this circuit, I need to compare this voltage, don't I, with this voltage, the voltage across the capacitor. In order to do that, I need a common reference phasor, or common reference vector. And the one I'm going to use is the current. Assuming I haven't got anything connected here yet, the current that flows around the circuit, this current here. I'll call that I. Let's just first of all draw it here. This is the current that flows around the circuit. I. And I'll just draw it as a single phasor like that. Now we know what the common, this is supposed to be a straight line, now we know what the common phasor is. If I was talking about the voltage across this resistor, whereabouts would it be in relation to this current?
Down. Voltage?
The voltage across the resistor.
Behind the 90.
With the current.
With the current?
With the current?
Yes.
In the resistor?
Yes.
I see
Yes, just the resistor for the moment.
Okay, with the current.
That's right. It's in phase with the current.
The current.
Call that VR. Now, yes, when we think about the capacitor voltage,
190.
yes, we see there's a 90-degree phase angle between the voltage across the capacitor, which, by the way, we're taking as our output, between the voltage across the capacitor and the reference current. And if we have a look at our capacitor circuit, we see that the voltage is behind the current by 90 degrees. So the voltage of the capacitor would be down here, wouldn't it? Call that VC. Does anybody disagree with that? Everybody follow that? Yes. What I'm saying is, whenever you see a circuit like that, the first thing you have to do is find out the common component. And the common component between these two is the current. If we just ignore anything that's flowing here, which we would do in practice, the current. So that's our reference. Now just remember your simple rule, and remember what we said here. The first thing is, if you were to measure the voltage across this resistor on an oscilloscope and compare it to the phase of the current, you would see it was in phase with the current. Always the case with the resistor, in phase. But if we look at the voltage across the capacitor, from what we said over here, they're not going to be in phase. There's going to be a 90-degree phase shift, shall we say, or phase change, or phase difference between the voltage and the current. So we can see from our little rule here, and from what we said with our capacitive circuit, that the voltage is actually behind the current. You've got to imagine these are rotating in this direction. So the current goes first, followed by the voltage. So the voltage is lagging, if this is going in the same direction, is lagging the current by 90 degrees. Okay? Now the next thing is, I want to know what the phase angle is between here and here. Well, I know what this voltage is. This voltage, the output voltage, is this, isn't it? But what about the input?
Higher. The input?
Yes.
VR.
No, that's the voltage across the resistor.
The input.
The input is actually the addition of VR and VC, isn't it?
Yes.
But notice there's a 90-degree phase. That's right. It's the vector sum, isn't it? What we call the vector sum. If I was to do that,
What plus the VR?
this is the input here. It's the vector sum of the resistor. Actually, you can do this by using the square law, Pythagoras square law, which says that this, right, we can think of this as the hypotenuse of a right-angled triangle. Okay, so we call this Vs, shall we say, Vs being the supply voltage. We can say that the square of the supply voltage is equal to the square of the two opposite sides of our triangle. In other words, Vc squared plus Vr squared. Yes, and of course Vs would be the square root of all this, wouldn't it? That's right, if you needed to find it out. Okay. Now, this is really basically how our vectors work in a complex circuit. A complex circuit is anything that contains more than one element. Here it contains a resistor and a capacitor, so we call it complex for that reason, complex impedance. If you were to put any figures into this, of course you could make it as easy or as difficult as possible. But for a start, in a practical circuit, we would know what Vs is. That's what we would normally start with. But how would I find out something like VC
I found VR first.
or VR?
I found VR first because
Well, to find VR, you need to know the current.
of the current.
Now, to find the current, you need to know not only the value of R, but you also need to know the value of
No, XC.
XC. That's right, XC.
XC would be 1.
That's right.
2,
Now-
CB.
XC,
What for the frequency?
yes, is actually equal to 1 over 2 pi times F times C. In other words, it depends on frequency. So exactly what these proportions are, what values we have here, doesn't just depend on the value of voltage or the value of resistance, it also depends on the frequency as well as the value of capacitance. Let me choose a simple example. Let's not bother with exactly what frequency. Let's say XC, in this example, this is just an example now. Let's say that, for example, XC is equal to R. The reason why I'm choosing this as an example is because this is a special example where XC is equal to R. If you remember, I mentioned this before when we did electronics and we were speaking about filters. And what did I say that was? At a certain frequency, XC is equal to R. The cut-off frequency, 3 dB frequency, yeah. Half power. Right, so we're coming back to this again.
Cut-off, not for the output.
First of all, if XC is equal to R,
No, it is voltage.
the voltage across the capacitor here
It is the same.
will be the same, won't it, as the voltage across the resistor?
No,
No, the output is the voltage across the
Is
capacitor.
the frequency, the current.
Yeah, the output will be the voltage across the capacitor. That will be the output. That's if XC is equal to R, then this length will be equal to this length, won't it?
Yes.
What can we say about VS then?
And what is 2?
Remember, if XC is equal to R, then VC must be equal VR.
Yes, then it should
Okay, so VS
would be 2 multiplied
is the root of, right,
2.
this squared plus this squared. Now, if these two are equal, then it's equal to the root of 2 times it doesn't matter, VR or VC, because they're both the same. The root of 2 times this. All right. If you wanted to know what the power of the output is compared to the power of the input, all right, this is the input, the output is VC. So this is input, VC is output. In other words, I'm taking the voltage from across the capacitor. Actually, it doesn't matter which you take, as they're both equal, but in this case, because it's a low-pass filter, I'm taking the voltage across the capacitor. If you take the ratio of these two, it'll give you output over input. All right? And if you take the ratio of these two, you end up with root 2 as being the output over input, root 2. Output voltage over input voltage. What is power proportional to? V squared. Does it not? V squared, power, V squared times R. Yes, output over input, right, is the ratio of VC to root 2 times VR. Do you agree with that? Root 2 times VR. Just put root 2 times VR there. It means the same thing. Therefore, the ratio of output over input, we can say V output over V input, is equal to VC divided by root 2 times VR. Now, VR and VC are the same,
Yes.
isn't it? So, in other words, the output over input is 1 over root 2. Sorry? Well, what I'm saying is, in my example, and it is just in this example, if XC is equal to R, then VC and VR are equal. Agreed? So I could put here VR or VC, it doesn't matter which one I use. Right? Now the ratio of output over input, I can take as my output here, in this case is VC, so VC divided by this, if this is my input.
How do you take square root of 2? How do you take only the square root of 2 out and the VR out?
I did it by changing this formula to this. Right. This is 2 times VR, isn't it? Squared. Yes. In other words, yeah. VC, it doesn't matter, these two are both the same value anyway, VR, so it's 2 times VC or 2 times VR squared. And then rooted, well, the root of VR is VR, and the root of 2 is root 2. So just keeping it as root 2. Hence, the ratio between the two is this.
1.41.
Yeah, this is 1 over root 2, or 0.707.
This is the gain.
This is the ratio of voltage between the output voltage and the input voltage. Okay? The ratio of voltage. All right? So when XC is equal to R, the output voltage, V output, from my filter, is equal to the ratio of 1 over root 2
0.7.
times the input, right, which is 0.707. Okay? But if I wanted to know what this is as a power ratio, I have to take the square of this, because the power is proportional to the square of the voltage. So as a power ratio, the ratio, what is 1 over root 2 squared? Yeah, 1 over root 2 squared is 1 over 2, isn't it?
1 over 2.
Yeah, 0.5. The square of this is this.
Yes.
So it's 1 over 2. So in other words, the output power is half the input power. Okay? We call that the half power point. And if you remember your decibels, in dBs, what does half power mean?
Attenuation.
It is attenuation, so it's a negative number Remember, multiplied by 2, it's 3 dBs.
Yes.
So we're dividing by 2, minus 3 dBs. So we call that frequency the half power frequency or the minus 3 dB frequency. Now let me just erase this and put the results of this on this side.
But we did it by other way, you know.
There's 2 or 3 ways you can do this.
We did it in the last week, I think, by different X.
Well, I haven't changed that. I've said if XC equals R.
Yes, yeah.
Well, that's all I've said.
Yes.
Now we can see how the frequency is going to be affected by this. In other words, if I gave you the value of R and gave you the value of
Change the
C, then you should be able to find out what frequency the half power frequency is for this. And this is a standard way of measuring, this is what we call, it's a standard way of measuring the cutoff frequency. Oh, not cutoff point, this is the cutoff point. If I was to draw a graph of this, remember that this is a low-pass filter, so we're going to get a graph something like this. Okay, this is our low-pass filter, where the output is plotted against frequency. At a certain frequency, the output power is half the input power. So we call this the half power point, or the minus 3 dB point, means the same thing. And that's when XC is equal to R. Okay?
cutoff point.
It's called a cutoff point. Now, it's not very clear as to why that's cut off, but what they're saying is, okay, it's a point in our graph. We say anything above that frequency, the signal is rejected. Anything below that frequency, the frequency or signal is accepted. I used these 2 words last week, didn't I, or the week before last, to describe the cutoff frequency.
Plus, here, slow pass filter.
It's a low-pass filter.
Yeah.
These are low frequencies, these are high frequencies. So we say that we get a better output power at lower frequencies and lower output power at higher frequencies. So another way of mentioning this is what we mentioned the other week, is we say that these have been rejected and this has been accepted. I used those 2 words, I think, when I mentioned this last week, when we were talking about filters.
Then we can see here, if it's lower than minus 3 dB,
Then it's say it's rejected.
then the voltage were rejected, the signal rejected.
Yes, that's what we say.
Is it higher than?
It's been accepted. Now this is just a standard level that's been, you know, universally agreed as to be the point, what we call the half power point of our filter. And in this example I've shown here, I'm choosing a low-pass filter. If I was to choose a high-pass filter, we would use exactly the same math. There'd be no difference in the way we calculate, except these would be the opposite way around, wouldn't they? In a high-pass filter, if it was a high-pass filter, it's just that we use capacitor here and resistor here. That's right, this is our input, this is our output. But we assume exactly the same calculation. Here there's no difference. XC is equal to R. And if XC is equal to R, then that's where our cutoff frequency is. Now I think we actually did a calculation, didn't we, at the end of the electronic.
But the difference would be accepted and rejected.
Yes, that's right. The difference would be the slope would be the other way around here.
Yes.
The lower frequencies will be rejected, the higher frequencies will be accepted. But we can always calculate, if necessary, what the cutoff frequency is simply by knowing what the value of C and R is. The cutoff frequency is when XC is equal to R, so
You know, we must know the value of C.
that's right, you do need to know it.
Oh, yes.
So what we're saying is 1 over 2 pi FC is equal to R. And what I want to find out is F, the cutoff frequency. So F is equal to 1 over 2 pi R.
CR.
CR, yes, that's right. If you needed to calculate that, I'm sure we did one like that. But the point I'm trying to make here is that we have 3 names to describe this frequency. One is called the cutoff frequency. The other is called the minus 3 dB.
Minus 3 dB is the cutoff point.
That's right, the cutoff point or cutoff frequency. And the other one is half power. There's 3 names can mean the same thing. You could, I've noticed in test questions they can use any one of those 3 names to describe that frequency at that point on the curve.
So that we said resonant?
No, I've not mentioned resonance yet.
Not resonant.
No.
This is just a
This is just a filter, simple filter,
cutoff frequency.
a cutoff frequency, yes.
Simple process was formula V S squared to power to 2 equal power to 2.
This one,
Yes.
this is to show how we call it the half power frequency. You get half the output power when X equals R. That's really what this proves. You won't have to prove this in the test, by the way. This is just for your sake, just to complete, to make sure you've got everything there if you wanted to prove to yourself. When VR is equal to VC, okay, then the relationship between the two of them, which is our source, depends on root 2.
Like we can find in the RMS.
Well, I'm assuming the current and voltages we're talking about here are all RMS.
Find the RMS from the
Yeah, but it's like that,
light that. Yeah.
but, it's not, we're not actually involving ourselves here with RMS. I'm just assuming it is all RMS values.
And so you can call it half power.
Yeah, 3 names, half power.
What these ones? Half
Yeah.
power.
Actually, I thought I'd given you this before, did I not? Or did I? Anyway, let me put it down just in case I haven't. So that you've got it down anyway. Yes, for a simple filter, that's true. Over 2 pi CR. CR, that is.
Not XCR.
No, CR. So cut off. Frequency at which the output power is equal to half input. That's essentially what we're talking about here. 3 ways of describing the same thing.
Same thing.
When the output power is half the input power, That's called the half-power frequency. And it doesn't matter what type of filter actually, and as we'll see later, even in tuned circuits we can talk about half-power frequencies.
Big frequency at white, which
At which the output power equals half input power.
I'm talking about voltage now or power?
Power.
Power ratio.
Yes, that's right. That's why we can use decibels. It's the square. It's the square of this, you see. So it becomes 1/2. We're using the square of the voltage.
the same thing means that
All of those mean the same. In a test, you might find any one of those three things, and you've just got to remember that they all mean the same thing. Cut-off frequency, half-power frequency, minus 3 dB
Can you
frequency.
say the high power frequency will be 3D frequency or
The high-power,
frequency? The high pass filter
high-pass filter.
will be 3D frequency.
Well, it doesn't matter what type of filter, whether it's high-pass or low-pass, you can still talk about the 3 dB frequency.
Still minus 3 dB.
Yes, always minus 3
High
dB.
or
Doesn't matter whether it's high-pass or low-pass.
the same.
The only difference, yeah, the only difference between high-pass and low-pass is, let me give you some examples of this. For instance, here, if we draw a high-pass filter, I can draw 3 examples of a high-pass filter. One like this. That's a high-pass filter, isn't it? One like this. And one like this. Right, there are 3 examples of a high-pass filter. All of them are high-pass, A, B, and C. However, they've all got one thing in common. They all use the same half-power frequency. If this is the half-power, this is power, right? Output compared to input. If that's the half-power point, they all have the same half-power frequency, which is this frequency here. The cut-off frequency. All of them are high-pass filters, A, B, and C, and they all use the same half-power point. The graph C would be one that's made from just a resistor and a capacitor. Graph B and A are more complex. We haven't done the sort of circuits, but they would be more complicated high-pass filters. If we do a low-pass filter, same thing, only the other way around. Again, we talk about the cut-off frequency. Only everything goes the other way around. We can talk about the same thing.
Or the accepted.
Right, now, of course, in the low-pass filter, the lower frequencies are accepted, and these are rejected. And here's the other way around. Here, these are accepted, those are rejected. There's the difference. Do you see that? Bad, okay?
His 3 names is for the high pass filter or the low pass filter.
Yes.
Cut-off frequency or half power.
Doesn't matter what type of filter, we can still talk about these 3 things. They're all the same.
And they become a question. The test give you multiple choice and give you circuit, high pass filter. or low-
Generally speaking, they're quite simple. There's very little calculation in the test.
No, they didn't ask you about this. What's the name of this?
Basically, what name of the filter
They don't
is.
say high pass or low pass.
You just got to look at the circuit to see whether you think it's a high pass or low pass.
Okay, don't put it in the multiple choice high pass or low pass. they put it.
Oh yes, like last time they put an
Yes.
integrator or differentiator.
Yes.
Yes, you must understand that as well.
They put name of them, of this three name, our cut-off frequency.
They won't put all those three together
No,
on one
only
answer.
one of them.
Yeah, one of
When you
those.
choose it.
Choose yes. If it points, if they might give you a graph,
Yes.
and they'll point to a point here and say, what is this? Is it the cutoff frequency or something else? But they won't give these three choices because they're all the same. You won't get those three as the same, and as the same choice in a. You can give any one of these, but not all three. We used to have questions in the test where they might give all three,
I'll give you
and then
first.
they'll say all of them are correct. But we've tried to avoid those sort of questions now.
Is the point cut-off frequency? The point.
Cutoff frequency, yeah. This F here, what is this? That's what we're talking about. Cutoff frequency, half power frequency, or minus 3 dB frequency. Okay, then that's great now. With a simple filter, then the half power frequency is when XC equals R, or when XL equals R. A simple filter is one with just one resistor and one reactance. Okay, either a conductor or inductor or capacitor.
Anyone on that?
These are all examples of simple filters. All examples of simple filters.
هذول صار فيه بدل راني
بدل الدي
بدل على كل ضغطة 10.
Problem? The mic is on, eh? Filters these are.
simple filter.
These are all examples of simple filters. A simple filter is basically a filter which just uses one reactance and one resistor. Simple filter. And as far as questions in any test is concerned, no matter how difficult the test, usually the filter is simple. If it needs you to work anything out, it'll be a simple filter. If it gives you anything more complicated, if it gives you a filter like this,
that we have in the paper that brought
that's a more complicated filter, and the calculations involved with this are much more complex.
sometimes
But you should be able to tell whether that's a low pass or a high pass filter.
from the scene here, from first.
Yes, just by looking at the design,
High pass filter.
it is a high pass filter, yes.
But we would sometimes put inductor and capacitor.
Yes, now I'm going to mention that in a minute. I haven't talked about that yet. We're going to talk about inductors and capacitors together in a minute. For the moment, for instance, this one here, what type of filter?
Low pass
Oh,
filter.
Dolo, what do you think? Low pass, yes.
Low pass filter.
A low pass filter. And this one,
High pass filter.
high pass filter.
High pass filter.
Another high pass filter. And of course, low pass filter. So you should be able to recognize these. This is an example of another high-pass filter, but it's not what we call a simple filter because it uses a number of reactances and resistances. It's a little bit more complex.
The half power frequency will change now.
Yes, we couldn't calculate that very easily. It would be more difficult.
But can we say it's cut off?
You can still calculate it, and when you do calculate, although it's more complicated.
No, I'm asking here. You said it's a high-pass filter.
Yes.
And the other theorem that you gave us before, the
Cut-off frequency,
cut-off frequency,
same as the minus 3 dB.
and the half power frequency.
They're all the same.
Also the same name.
Exactly, yes. That doesn't make any difference on the type of filter. That's any type of filter.
The difference only will be when the cut-off.
Yes.
Imagine.
Here it would be more difficult to calculate what that frequency is going to be. Here it's much easier. And this is basically, if you need any calculation, you're not going to get more difficult than that. But what I'm trying to say here is you can get filters which are a lot more complex. Right? But you should be able to just recognize by looking at them like this would be a high-pass filter. It's just a more complicated version of this, isn't it? Like one filter after another in a sense. Now let's look at some special circuits involving inductors and capacitors. Here we just used a reactance with a resistance. Reactance with a resistance in all cases. A single reactance with a resistance. Now if we look at two reactances together, we get a different circuit altogether. Let me just erase this.
Okay, when you put the dishes, you can bigger as a amplifier.
Well,
For
can
transmitter.
you ask me that? Yeah, can you ask me that again when I talk about gain tomorrow? Remember the word gain.
With transmitter and receiver both? Or
Both of them, yes, exactly. Both of them. You get gain in the transmitter and in the receiver if they both use directional antennas. Yeah.
Can it be to use as receiver and transmitter at the same time?
You can. Yeah. In fact, that's exactly what happens on our point-to-point communication using microwaves. Using the same antenna, we can use it for transmitting and receiving.
Two positions, this is the point. Two positions, take the...
Well, what I want you to think about here is using it just for one reason, either as a transmitter or as a receiver, not both. They can actually be used for both, but if it's used as a transmitter, that's right, exactly. If it's used as a receiver, it receives the radiation from the other side, wherever that is, goes to the reflector, and that concentrates the beam onto the actual antenna, shall we say, which is here. Yeah. The principles are quite straightforward. It should give us a very narrow beam, but because it's not perfect, we are going to get side lobes. They call them side lobes. And that can affect us if ever we're involved in aligning. Now, the reason why data guys are going to be involved with this as much as radio is because our microwave link handles telephone calls and data. All right? So the telephone and data people are very much involved with that microwave link. It's them that people come to if anything goes wrong, not the radio guys. It's the data guys. So they need to be able to handle this.
Wind can affect it.
Yes, indeed. In very bad weather, bad weather has two effects on it, but wind, if you take wind, if it gets very windy, it can move. And don't forget, you don't need much movement. A small change in the position of your antenna, just a small change, and it's gone, you lose it. It's gone off to a different direction, isn't it? So if you get very windy conditions, the antenna can move a little bit. So then you've got to be able to bring it back again to get it focused again onto the...
Can you repeat what's the Side loop.
the side lobe.
Why it is coming?
It's coming because we cannot have a perfect reflector. A perfect reflector would mean I can transmit from a point here to here, but this is in the space by itself with nothing connected to it. Well,
And not only that, this also would reflect something.
yes, that's right. Yes, even the point itself is going to interfere. Anything in front of that wave, anything that goes in front of that beam is going to cause small amounts of energy, if it's a transmitter, to be radiated in other directions. And that will produce a side lobe. Now, in actual practice, of course, we can't just have a point there with nothing on it. It's got to be physically connected to something. So we usually have some metal structure here to hold. In the case of, for instance, a TV receiver, we call it the LMB, don't we? And that's right in front of your dish. So you're going to have reflections off this structure.
When the size of the dish is bigger,
Mm-hmm.
the focus of the signals will
Yes, we get a narrower.
narrow focus.
Yeah.
Stronger for
The smaller the dish, the wider will be the.
stronger. Can the signal be stronger or only narrow? What voltage in the arm?
Well, if we have a look at the circuit, depending on the value of current, we're going to get a voltage across the inductor, voltage across the capacitor, and a voltage across the resistor. So the first thing we need to do is have a look at the phasor diagram. That's the first thing we must consider when we're looking at something like this. Beginning with the current, because the current is the same through all components, so that's our reference. And all we have to do is have a look at how the different voltages are across the different components. First of all, the voltage across the resistor. Okay.
Okay.
That's going to be, what's the phase relationship?
The same.
Yes, in phase with the current.
Yes.
That's VR. Okay. What about the voltage across the inductor?
The inductor will be 90
degrees out of phase. Is it going to lead or lag on the current?
lead.
Lag.
Remember our...
The voltage lead in the
Voltage lead in the
inductor.
Inductor, but lag in the force.
Yes, I'm talking about the inductor now.
Inductor lead.
Lag.
In the inductor, the voltage will lead on the current.
On I, it is lag.
Yeah, okay. I asked what the voltage was doing, actually. Okay. VL is in that direction. Agree?
Yes.
And of course, VC
Will be lag.
is the opposite. Now, this is where the difference is. The complex impedance is actually the vector sum of all three of them now, not just two of them, but all three connected. But look at these two voltages, the voltage across the inductor and the voltage across the capacitor. This is VL, across there, and that's VC. They're completely in antiphase, aren't they?
Yes, divine, not here.
Right, antiphase. Now, so therefore, if I was going to add these three together, the first thing I want to do is take the difference between these two.
Zero.
Well, if they're equal, it will be not necessarily equal.
Here it's this is actually zero. And we are maybe will have that.
Well, all right, let me just redraw it a bit.
Change it.
Right. It's not necessarily zero, in other words. It does depend on the reactance of L and the reactance of C.
C and 6.
That's right. But in order to find out the complex impedance, we have to take the difference between these two and then add it with the resistor, just the same as we did in the other circuit. Okay? However, as far as you're concerned, we've tried to make things a little bit easier for ourselves here. Whenever we see an inductor and capacitor together, we're usually interested in what is called its resonant frequency. Now, it's a special case at resonance. Resonance means that the value of XL and the value of XC are equal, are the same,
Same.
right? So by definition, resonance XL is equal to XC. The reactance of the inductor and the reactance of the capacitor are the same. Of course, this depends on the values and also the frequency, doesn't it?
But doesn't depend, must have the same frequency.
Must have the same frequency.
But then to have the same frequency, that we change the value of the L and the C till we have the.
Yeah, well, I know what you mean, but don't confuse things here. I mean, we can draw a very simple equation here. What is the value of XL? How do we find that?
2 by
1 over 2 by
No.
L.
2 pi FL.
FC.
Frequency L.
2 pi FL.
Yeah. And
Right.
the C will be.
And XC.
1 over 2 by FC.
That's right. Notice that as the frequency changes, the reactance of the inductor gets bigger. The reactance of the capacitor gets smaller. Actually, what's actually happening, if you were to draw a graph of frequency, one gets bigger, the other gets smaller.
Yes.
But there'll be one frequency where they're both the same. At a certain frequency, both XL and XC equal.
But we have fixed
Groups
frequency here.
Right, well, if we have a fixed frequency, then what we've got to do is find out what that frequency is. Right? So what we do is we use this formula and we make F the subject of the formula. That's just pure math. Now, without going into the details, that goes
Multiply with that.
F equals 1 over 2 pi, right, root L times C. Have you all heard this formula before? This is for a resonant circuit. F equals 1 over 2 pi root LC. You needed to calculate the formula.
This frequency is the frequency that when XC
Is equal to XL.
have the same frequency as you said here.
Well, as far as you're concerned, in any given circuit, you've only got one frequency at a time, or let's say the supply frequency or whatever it is, of the signal that we're using. You only take one frequency. And we see what the condition of the circuit is at that frequency. Well, of course, then we have to use this formula here. All right. Now, of course, not at all frequencies is XL going to equal XC. Some frequencies it won't.
That's what I'm saying.
Yeah.
You measure, calculate the frequency first, and divide the frequency different from the source.
No, the no, be very careful here. Frequency at every place in this circuit is the same.
No, I'm saying we calculate this frequency.
Yes.
That XC equal XL.
XL.
Yes. And you want, as you said here, this will have XC, XL equal to C.
Well, that depends. I mean, yes. There's 2 or 3 ways around we can have a question here. One would be if I give you the value of L and I give you the value of C, and I said, okay, those are your 2 values. What is the resonant frequency? You see, and then you would have to use this formula, wouldn't you?
Can you give me the 2 L and C and say this circuit, is this frequency?
Is it resonant? Is
Can
that
you
the
give it the
question?
frequency from circuit? This frequency is resonant frequency.
What you're saying basically is, if I give you 1, say L,
Yes.
and I give you the frequency, can you find C?
Yes.
Yeah, of course, there's 3 unknowns, isn't it? There's L, C, and F. Any 2 of those, you should be able to find the other one. That's essentially the bottom line. But we've got to also think, what's the most common way in which we could use this? Now, the important thing about resonance is that VL and VC in this circuit will be equal. Okay? Do you agree with that? The voltage across the inductor, since the current is the same through both of them. Yes. If XL is equal to XC, then VL must equal VC. So what is the total impedance of the circuit?
Total
Just R.
impedance?
Yes, just R, because the impedance of the circuit depends on XL and XC and R, doesn't it?
Yes.
But XL and XC
Same.
produce back voltages which are opposing one another,
Yes.
so they cancel.
Cancel each other.
So the only impedance in this circuit is just R.
And the output will be in R.
Yeah, basically it's just R, you see. That's called resonance. And in fact you can draw here, for example, if I was to draw a graph of the current, put this in a different colour.
It's phasor circuit, this one.
Sorry?
It's called phasor circuit.
This is a phasor diagram.
Phasor diagram.
Yeah.
What
This is,
about
not,
this
this is a resonant circuit.
Phasor circuit?
Resonance. This is what we're talking about here,
When we
resonance.
can use it?
Well, we'll come to that in a minute. If you're drawing a graph showing the current against frequency, it should become clear here what's happening. At resonance, okay, we get a certain value of current flow around the circuit which is equal to the voltage supply divided by the resistance. Do you agree with that?
Yes.
Because remember, these two reactances effectively cancel one another, don't they? Their back voltages are opposite, so we can ignore them. And the only current flow that flows will be the current V over R. Now let's say I had a variable frequency control on this, and that's really what we've got to think of now. What happens if I increase that frequency?
Increase, the L will, C will.
XC will go high.
XL will go high,
And XC will go low.
XC will go low. So now, right, VL will be bigger than VC.
Yes.
Now, of course, we've got a complex
The
impedance.
same that you have VC to the power to 2.
It's as though now we've started to increase XL, and now we've got a complex impedance. So the total impedance will increase in the circuit. We've now got XL as well as R.
Yes.
So what will happen to the current?
Current will increase.
No. If we increase the
Decrease, I
impedance,
said decrease.
Decrease.
Because you increase the
That's right.
current. And,
because we've increased XL. Now, if we decrease the frequency below the resonant frequency, the opposite will happen.
XL it is decreasing.
Decrease
It is increasing.
will increase. Again, we get a difference between the two, only in the opposite phase. Our total impedance will be the sum of our complex impedance, and therefore, again, reduce the current. So we get a waveform of something a little bit like this, whereas this frequency
This is about
is resonance.
current in R now you are talking?
Current around the circuit. There's only the one current at the moment. And we call that the resonant frequency, and that's what happens at resonance. FO is the resonant frequency. Maximum current around the circuit. Okay. And the current will decrease either higher than or lower than that resonant frequency. Either higher or lower, we'll get a decrease in frequency.
Resonant frequency is PFO.
FO. Yes, on diagrams you'll see FO being used as the symbol for resonant frequency.
I will be B divided by R, XL or XC.
Yeah, if you really wanted to work it out, we don't need to do it here, but if you wanted to work it out, then the current will be equal to the supply voltage divided by the impedance of the circuit. Now, the impedance of the circuit is equal to actually the root of x squared plus r squared, where x is the difference between XL and XC,
Yes.
whichever one is bigger, you see. Now, of course, if XL and XC are equal, then this value of x becomes 0, So then it's the root of R squared, which is R. And that's what happens at resonance. I've never seen any questions in any test which actually to work that out, although it's not difficult, it's just that they don't usually ask that in a test. All you need to know is resonance. And what resonance means is when XL and XC are equal. They're equal, then that's our resonance circuit. This little universal graph here shows what happens at resonance above and below resonance.
XC or XL?
X here is XC or is the difference between XL and XC. I just called it X, whichever one is bigger. If you use this sort of circuit, an L, a C, and an R, is this going to be a high pass or a low pass filter? Do you think? It is a tuned circuit, and so therefore we can't say whether it's high pass or low pass. But what we can say, if you have a look at this diagram here, it's like a band pass. Band pass. Now this is a different thing altogether from our simple circuits. In a bandpass filter, we have two cutoff frequencies, don't we?
Yes.
One above and one below the resonant frequency. These are this is our half power point, and these are half power frequencies. So this would be a bandpass.
امسح كله.
So why do you think we call this a band pass
Band?
in this example? Okay, well remember how we defined a high pass filter and a low pass filter. We said all frequencies higher than a certain frequency accepted, or lower
Only
rejected.
the band pass.
Right, we say that frequencies between these 2 points are accepted, and lower than F1 or higher than F2 rejected. So it's a band of frequencies, difference between. You can understand now how important these circuits are, because when we want to restrict a band of frequencies in a circuit, we very often have to use tuned circuits to do this. Tuned circuits would be needed for band pass filters.
Can use it for different frequency that we have divided it.
You want to cut out one frequency and accept? Yes, you can. That's a very good point. I mean, if you had, say you had a receiver,
Yes.
and you wanted to receive this frequency, but you've got other frequencies above and below which could interfere, right?
You put this band pass.
That's right. You put this band pass filter over the frequency that you want, and if it works correctly, then these other two frequencies should be very much reduced, or rejected is the word we would use. Rejected. These would be rejected, that would be accepted.
Is it commonly called bandpass filter or just tuned circuit?
Or what? Sorry, what was the second? What I'm saying here, just to keep it quite simple, this is a tuned circuit, right? There's no doubt about it. But what I'm saying here, we're using this tuned circuit as a bandpass filter. Now, there are different ways in which you can use a tuned circuit. Another example of using a tuned circuit is in an oscillator. In an oscillator. But here, we're using it as a bandpass filter. Yes, you can use a tuned circuit in an oscillator too. But here, it's just the way we're using it as a bandpass filter. And again, there are different designs of tuned circuit. Here you can see clearly that we've connected our inductor and capacitor in series. But it is actually possible to design a tuned circuit where you have your inductor and capacitor in parallel, not in series. So let's have a quick look at that and see how that works first. The mathematics involved is just the same, not a lot of difference, but let's just draw the circuit. If I was going to draw the phasor diagram for this circuit, what do you think the reference phasor should be, a voltage or a current? Voltage.
The reference?
Yes.
Voltage.
What you've got to think of in the reference is what is going to be the same through
The
both.
same current.
It's the same voltage across both,
Yes.
but it's not necessarily the same current, that depends.
No, current different.
No,
It could be different, yeah. So we begin with our reference phasor voltage. We'll call that Vs. It's going to be the same as the supply in this case. That's our reference. And we can still use our little reminder here for phase. First of all, let's have a look at the current through the capacitor. IC. Is that going to lead or lag on that voltage? Yes, according to our little formula here, it's going to lead on the voltage. That's right. So I can put an IC there. And if we took the value of current through the inductor,
Good night.
the current through the inductor is going to lag, isn't it? That's quite correct. If you were to measure the current here, this current, IS, the supply current, according to this diagram, how would you find it? IS, this current here.
Can you use the same ES equal power to 2 equal to
Now wait a minute. Before we answer this, have I got any resistance here?
No.
No, I haven't shown any resistance, have I?
Yes.
So there's no complex impedance involved. There's no roots and all the rest of it. The question is, if I wanted to measure this current, how would I find it if assuming I knew all these values here?
First compare the XL and XC.
Find that.
You know the current? Let's say this current here is 100 milliamps.
Yes.
This one's 80 milliamps. And the voltage is 10 volts. Now, how do I find this current?
Adding 20.
The total impedance. The current, the total.
20 milliamp.
Yes. Essentially, yes. We're not trying to make this any more difficult than what I've shown you. It's the difference between these two, isn't it? This current is the difference between that current and that current.
100.
So if I have 100 milliamps, if this is IC, and IL is 80 milliamps, then the current here will be the difference between the two,
20.
which would be 20 milliamps.
What if you put some resistance inside? Adding.
Oh, wait, we'll not put the resistor in at the moment. Okay, just currents. So IS is actually equal to the difference between IL and IC. This little symbol here means difference between. Whichever one is bigger, subtract the smaller one from it.
This concept is done for motors to reduce the loss of power. Because
Oh, you're talking about power factor?
yeah, the power.
Power factor. Yes, you can use it in power factor. But what I want to mention here now is the special case, because that's what this lesson is all about. What happens when XL is equal to XC? Because that's what we called resonance, wasn't it?
Yeah.
Now let's have a look in this circuit when XL is equal to XC.
Same current.
This is resonance. Now, first of all, you said something about the current. What did you say about the current?
Divided.
The same.
Divided to 0.
Yes. What we're saying is IL and IC are equal.
The same current.
Same value.
Same value, not the same current.
Well, same value of current.
Yeah.
But they are in opposite.
Okay, listen to me. If we have 20 milliamp,
Yes.
this take 10 and this take 10.
No. No. That's not true.
Nothing but
Yeah, but look. This is our vector. This is our phasor diagram. They're in opposite phases. Okay? When the current is increasing through here, it's decreasing through here. When it's maximum here, it's 0 here, and so on.
So no current will flow.
Exactly.
No current.
No current will flow here.
One cancel
0
the
will
other.
be higher.
Yes, it cancels the other, exactly.
0 then.
Yeah. So at resonance, when we talk about a parallel circuit like this,
What about in the series? Same I equals IC equals.
no, wait a minute. Let me just finish this first, because you're going back now, and we're going to get totally confused if we're going to start talking about them both in the same breath. IX is equal to... one thing about resonance, doesn't matter what the design of circuit, XL and XC are equal. But in this circuit, if XL and XC are the same, we have the same voltage across them both, then the two currents must obviously be the same. Same voltage, same impedance. But we remember the currents are 180 degrees out of phase. So therefore, if that current is equal to that current, this current would be 0, wouldn't it? Okay. So if I was to draw my little diagram again, showing current against frequency, right, at the resonant frequency, which I called FO, remember, the current through the circuit is 0, or almost 0. In fact, it won't be quite 0 because there will be some power losses due to resistance and all the rest of it. So it'll be a small current, but in theory, very, very small or 0. And anything other than the resonant frequency, then XL and XC are no longer equal, and we'll start to get an increase in current IS. So we get something like this. If you look at this diagram, it's very similar to the other one, only the opposite way round, isn't it? Very similar. And we can still talk about half-power points, although we haven't calculated them, it's not necessary in this course, but nevertheless we can still talk about them. F1 and F2. Now, you used a word, what word did you use?
Accepted.
Sorry? Yes, it's a rejector, isn't it? Remember the other one was a band pass filter. We called it a band pass filter.
This is band rejector.
This is like a band stop or a rejector. So there's 2 or 3 names that can be used to call the same thing. This you can call it a band stop filter. Or sometimes the word rejector is used because it's rejecting a band of frequencies. So sometimes we can call it a rejector circuit. A band stop or rejector circuit.
Band stop filter.
Or band stop filter, yes, I should really put that in filter. So it does depend on how we connect our inductor and capacitor, whether we're using it as a band pass or a band stop filter. In both cases, XL equals XC at the resonant, for the resonant frequency. Now we have to see what type of filter it is, whether it's a band stop or a band pass. Now we have not calculated these 2 frequencies. We haven't calculated that. That's a different calculation, it involves different things altogether. And we don't actually do the calculation for these 2 frequencies, the half-power frequencies. These are the 2 half-power frequencies. Not for complex circuits like this.
to the cutoff.
They're the cutoff frequencies, yeah, exactly. Cutoff, or minus 3 dB.
Or 3 dB.
Remember, any of those three expressions can be used to explain what these two frequencies are.
Power frequencies,
Hmm?
Cutoff
half power
frequency.
frequencies.
Yes,
Half
half
power
power. Remember, there's
frequency.
3 definitions.
Yeah, but from other.
Yeah.
Yes, this one.
This is frequency again here, you see. This is current. At a certain value of current, that's the half power.
Yes.
Whatever that is, depending on the rest of the circuit. But these two frequencies here are the half power frequencies. We assume that this point here is the half power point.
What's the three names? Half power?
Half power,
Yes.
minus 3 dB point, or minus 3 dB frequencies. That means the same thing, of course, from our knowledge of decibels, and cutoff frequency. All of them mean the same, exactly the same thing.
Power circuit.
Excuse me. Is different, the current different.
Yes, this
between
little
I
symbol
and
here means the difference between the two. Now,
Not يعني not I is the total current.
it is the total current here,
Yeah.
but you can't just add these two together. I mean, I might have 6 amps there, 6 amps there, but this is 0. It's not like ordinary parallel circuit, is it? Very different,
That's
because of the phase difference, that's right.
That's total zero.
I total distribute the I see and.
It's the difference between these two currents. So individually, these currents could be quite large, but this could be almost 0. Yes?
If you hear about this one, you say it's the frequency that in CAL, because it's going, the power is going low.
Well, don't read anything into this than you have to. FO is by a different definition the resonant frequency.
Equal to XC.
That's when XL is equal to XC. And then we have a frequency above that and below that, which are the half power frequencies. What their difference is a calculation which we haven't involved ourselves in yet. But this is the resonant frequency. And that's all I've said so far. I haven't given you anything else other than that. But that should be clear that we have a type of band stop filter here. And in our series case was a band pass filter. So whenever we get an inductor and capacitor in a circuit, we're talking about a band of frequencies if we're using it as a filter of some description. Okay.
Band pass filter
Or band stop filter. That's right.
But we got single, either resistor or the capacitor, resistor with the.
That's a simple filter. With a single reactance and a resistor, it's a simple filter. Either low pass or high. As far as you're concerned, in any questions in an exam, it'll be. Do you have another question, Fazal, you wanted to?
About the current in the series.
Yes.
You said the current is common.
That's right. In the series circuit, we took the current as the common. And what we did actually do is take the two differences of voltage in order to give us the results we wanted. Here, the voltage is common, and we took the difference in the two currents to find out what's going on in the circuit.
Because PL equals the
The difference in voltages in the series circuit,
I mean, no, the resonance frequency when the FC equals
XC equals XL.
and VC equals VL.
Yes. Here, IC and IL are equal. In there, it was VC and VL is equal, yes. Now, you should be able to recognize also circuits like this and answer very simple questions on it, nothing too complicated. Have a look at this.
Allah
وانت قاعد تسوي تو يجي يحسب الوقت بتاعنا بنصير فيه احنا اليوم هذا بنصير بعد الفتح. اللي بيجي جنبك كذا هو
دحنا الكلاس بالجنس
ايش اليوم سويت؟
لا وين درجة نيو باس فلتر rejected this
سجلت
It's okay, I'm trying to pick up what's going on here.
يمسك عليك
I think I should need, I tell you what, I should have another camera pointing to you, shouldn't I? Circuits is, are they band pass or band stop filters? Which one is which and why? Or are they high pass or low pass filters?
the first one looks like اسمه ها no low pass the first one
Low pass.
first one as a low pass filter
Is it? Imagine then two questions in a test and you've got A, B, C and D.
high pass
Low pass,
the first one high pass
high pass. This is a
Stop
good
pass.
question. Band pass
band pass
high
band
pass.
stop
or band stop.
يلا حبايبي تعال.
There you go.
High pass.
Multiple choice question, 4 answers, all of them different, only one of them correct. 2 different questions, question 1, question 2. And I could give the same number of selections for each. Which
One
one's
high
good?
pass. C and D one high pass one
C and D. Oh, you mean C is number 1
Yeah.
and D is number 2? I'll wait until, has anybody else got any answers yet?
number one high pass
You're still sticking with your high pass, are you?
sticking yeah
Wow, you're a brave man. Think about
D,
what we've got
what
here.
is D? Band stop.
تعال stop.
if we think about high pass and low pass, in the examples I gave you before, if that was the circuit,
Low pass.
it's a low pass filter.
Yes.
If that was the circuit,
Hi.
high pass filter.
Uh,
Now we've got a high and a low.
that's it so you all take
So-
certain band pass
band pass.
Well,
band stop
Band bus.
to answer these problems, think about resonance. What happens at resonance? Because remember, when we talk about band pass or band stop, we're talking about above and below a certain resonant frequency. So if we know what happens at that resonant frequency, we should know what's happening between those half power frequencies. And in both cases, we've got to look at what happens at resonance. What would happen when XL is equal to XC? What happens when XL and XC are equal? When we answer that, we'll be able to decide whether it's going to be a band pass or band stop.
It is
It's
band
band
Well, first of all, let's try and eliminate 2 of these.
Yes.
Is it going to be either a high pass or a low pass?
No.
No. And the reason for that is because we've got C and L.
Yes.
Whenever you see C and L in a circuit like this I'm talking about, not like this. If I have something like this, that's a little different. That's different. That's not the same thing at all. But I'm talking about this. What I'm saying is another thing here. It's most common to see inductors and capacitors connected in parallel like that. It's a more common arrangement than in series. But anyway, this is our situation. Let's have a look at question number 1. At resonance, think about at resonance. XL and XC are equal.
Yes.
Now remember what we said here. If XL and XC is equal, what's this current?
No current flow.
Almost zero current. In other words, it's like the impedance of this is very, very high, gone to a very high value at resonance.
Yes.
If there's zero current here, what's the current through here?
Lower current.
Zero. Yeah, they're in series. They're in series to the input. That's right. So it's like this impedance becomes very high at resonance. High impedance at resonance. And therefore, very high compared to the resistor, very low voltage here. But if you go below or above resonant frequency, then we start to get current through there. And therefore current through the resistor. So the output will increase. So if you imagine it, it's like this sort of,
Band stop.
which means a band stop.
Band stop.
Band stop filter. Remember, we've already eliminated these two guys.
But we want the output.
Yes, the output is across the resistor. And the output in this case is really dependent on the current that flows. It depends on this. The bigger the current, the bigger the voltage across the resistor. We're not going to go into any actual calculations here, just physically what's happening as we change frequency relative to one to another. So this is the sort of output we would get. So the answer to 1 would be C.
The frequency, you said it is the resonance shall have the
D, not
Sorry, D is it? Band stop. Sorry, my mistake. D.
D.
Sorry about that.
Yes,
Yes, sorry about that.
zero.
مفتاح يعني هو.
Almost zero.
Almost zero at resonance. So therefore the voltage across here will be almost zero at resonance. And this is our output, remember? This is the output from the circuit.
Yeah.
But when we go off resonance, the impedance of this decreases because we start to get current flow. So now our output voltage will increase either side of the resonant frequency. So that gives us a shape of a band stop, doesn't it? Filter. Or, instead of D, but not as well as, instead of D, they could have said rejector circuit. Remember I gave you two ways of describing this circuit, a band stop circuit or rejector
It's
circuit.
rejected, yes. Or a band pass or
The same.
the same يا جماعة.
Band pass and rejector.
لا
No,
same.
this is band pass, this is band
لا band
stop
stop
or rejector
band-
circuit.
yeah, the same.
Same.
يلا يمين.
The same.
These two are the same,
Yes.
but not this.
This one band pass are accepted.
Oh, okay. I didn't actually use that, but yes, okay.
So accepted.
Accept.
تبغى تقول نفسها البقى ستوب
عارف.
نفس الريجكت.
This is less common, this one, though. But this is less common. This is common rejector circuits. It's quite common. Usually you would just call it a band pass filter. Okay, that brings us to number 2.
Yes.
Now again, we've got an XL and XC in parallel, so we use the same theory. What happens at resonance? What's the current through there?
There is current.
Maximum current.
No,
Zero.
the total current.
Total current.
maximum.
Wait. Let me ask you again. The current through here and the current through here at resonance are equal,
Zero.
right? So this current through here, if I is zero. What's the voltage across this resistor?
Yes. Only resistance.
total.
The output.
I total pass in the resistance.
The voltage across the resistance?
Yes.
The outputs.
No, the output voltage is here. What's the voltage across the resistance?
I total.
If this current here is zero, and there's nothing connected here for the moment, zero voltage across the resistor. So the output voltage will equal the input voltage.
Same.
Same as input voltage. Yes.
Output.
Now, what we've got to consider then, so the output voltage, the output here, is going to be some value which is equal to the input voltage. Right? But the next thing to consider is, okay, what happens if I increase or decrease the frequency? Well, if you increase the frequency, you're going to get more current through the capacitor, less current through the inductor, and therefore you're going to get an increase in current through the resistor. An increase in voltage across the resistor, what happens to that voltage? Must decrease, because that's got to be subtracted from your supply. So you actually get a reduction in voltage. And the same if you decrease frequency, but this time because of the inductor current. So here, bandpass filter, which of course is C.
Then from the circuit we have here, inductor and capacitor in parallel.
Parallel, yes.
You see it without resistor, it's band stop. Without resistor.
Yes, you've got to be careful. See, in this way I explained here,
Yes.
I explained it, that's right, I explained it without any resistor
Yes.
and just talked about the current flow, about whether it's a band stop or a band pass.
Excuse me. The first point here, we have resistor, and during IV, there is voltage in the input. Voltage pass through the resistor should be there is current.
Now what I'm saying at resonance, if you find out what's happening at resonance, that's going to tell you. At resonance, this current is 0, right?
Yes.
If that current is 0, this current must be 0. Because that's the only path there is for the current on the input circuit.
Yes.
If that is 0, VR must be 0, which means the whole of this voltage will appear at the output. Maximum voltage at the output.
Okay. That parallel circuit, small parallel circuit, there is 0 current there.
Yes.
The same, the first one, there is 0 current in.
Yeah, but because of the position of this, remember it's all to do with the position in the circuit. Because of this is in series with your output, not in parallel,
Yes.
then because of that, this becomes a band stop filter. Because at resonance, 0 current through there, 0 voltage across here. You see, basically that circuit and this circuit are very similar, except here,
What's the main difference?
the difference is here we're taking the output from across the resistor. Here we're taking the output from across the tune circuit. Look at your...
ايش اللي فرق بين هذه وهذه؟ هذا
If I have...
الحين خلينا نمشي الصباح الله
If I have a circuit like that, if I took my output from across here, across the capacitor, is that a high pass or a low pass filter? But this is the input.
voltage.
I took my output from across the capacitor.
This high.
If I took my output from here, and the input is here, is that a high pass or low pass filter?
Low pass.
Low pass.
Low pass filter.
But if I took my output here, instead of here,
Will be high.
a low pass filter. Sorry, it's a high pass
High
filter.
pass.
The opposite.
Yeah.
Same here. If I took my output from across the resistor, okay, it's a band stop filter. But if I took my output from across here, which is what I'm doing here really, it's a band pass filter.
Band stop.
This is band pass, that's band stop. So it depends where you take your output.
Maybe if you only one circuit and this circuit, we get the output from this one.
Yeah, they've got to really show you where you're going to take your input and output. That's true. They should really have this or this arrangement in order to ask you whether you can recognise the band stop or band pass. Which is one of the uses of a tune circuit. What we've got to talk about next, after we'll stop in a minute. What we're going to talk about tomorrow is tune circuits and how we use them in oscillators.
Band pass so that we get the current, the maximum, the resonance.
In a band pass,
Yes.
this is a band pass, isn't it?
the current.
The current at the output, the voltage at the output is maximum.
I mean resonance.
Oh, there's maximum circulating current, but this is zero current at resonance. Whenever you get an inductor in parallel with a capacitor, the current through both of them becomes almost zero at resonance. It's a series circuit where you get maximum current. They're not as common. That's the reason why in these two examples I chose parallel inductor capacitors. And using those together with the resistors, you can use it either as a bandpass or a band stop, depending on how you connect it. Okay. Have you done this before?
Yes.
You're telling me no? Have you done it at all before?
No, we didn't.
هذا ما
But it's not clear. Take it as it is.
Yes, this you should have done something on this before at some time if you've done basic electronics.
This is the basics.
He doesn't want to be on camera and saying this. And in order to get that signal up to the dish, you have to use what is called a waveguide, which is basically a metal tube or metal guide. Quite an expensive arrangement, usually used for high power or maybe radar installations. The most common arrangement for communications is this, where the microwaves are generated in front of the dish. They're actually generated here. They're not generated remotely. So you have part of your transmitter is actually here, in front of the dish. And it's the same for the receiver. Here, the received microwaves are focused into the horn and then they're directed down to the receiver in this case. Here, we have the receiver here. This is where the microwaves are received and then they're changed to a lower frequency signal to go down a cable. In the case of a TV satellite, this would be called an LMB. Low noise points I mentioned, propagation and types of antenna. We'll have a break now. After the break, we must talk about decibels. Okay? Actually, we do have a printout of some of the main points we're going to cover in this lesson on one of the pages that I handed out. But let me just go through it on the board and then we'll see what we're talking about. Basically, what we're talking about here is a measurement of ratio. Now, what do we mean by a ratio? The word ratio. Yes, it's one number divided by another, basically, isn't it? You can talk about ratios in a number of different ways. Usually you talk about the ratios of two items or two values which are the same units. For example, you can talk about the ratio of voltages, or the ratio of currents, or the ratio of power. Now, when we talk about decibels, we're talking about the ratio of power. Okay. Let me give you an example of that. Let's take an amplifier as an example. Let's say it's a power amplifier, a PA stage. PA meaning an abbreviation for power amplifier. Okay. I have an input and an output. I can measure the power going in and I can measure the power coming out, can't I? Assuming I have all the information. So we'll say power in and power out. Okay. Now, when we talk about the gain of an amplifier, this word here, gain, what do we mean?
Be fine.
Output divided by
The ratio of the output.
The ratio of output over input.
Yeah.
Yes. Now, be very careful with the word gain. There's a technical definition of gain, which you should all be aware of. The word gain means to get something. Now, let me remember when we spoke about amplifiers first time, I mentioned about transformers. Remember, this is a side, this is not part of the notes. Remember in a transformer, I said you could have a transformer something like this, where you could have, say, a step-up transformer, 1 to 2. So I put a signal in here. Let's say the signal is 1 volt peak to peak. What's going to be the signal here? 2 volts peak to peak, isn't it? Okay. Now, the first question is, what is the gain of this transformer?
2.
One.
We don't use it as a gain.
Right, so what is the gain?
1 to 2.
What has this signal gained?
Nothing.
Nothing, yes. Gain actually means you must get something, you know, something has got to be added to the signal. Nothing's been added. All we've done is change the ratio of voltage to current, really, haven't we? We haven't added any power. When we talk about gain, we've got to speak about power. So in a transformer,
It's both the same.
yes, the power output is equal to the power input, isn't it? So there is no gain in a transformer. And this is an important point I want you to try and get clear in your mind, the concept in your mind about what we mean by gain. To gain something means to collect something. Like if somebody give you 1,000 reals and somebody else took 1,000 reals from you, what have you gained? Nothing. Okay.
Can you say the multiplier?
Well, yes, okay, but basically what we're having to do, in the case of a transformer, there is nothing added in the way of power to the signal, is there? The signal coming out, power-wise, is the same as the signal going in. All we've done is change the voltage, but voltage isn't power. Right? It's like if I had here, say, 1,000 reals in 100 real notes, and then I got a mirror, so it looks as though I've got 2,000 reals, because you can see it twice. But there's nothing, it's all a trick. It's not real. You've not gained anything by that.
But the gain means the power.
This is a fact that your
No, power-wise, it appears, power I'm talking about now, reality, as opposed to the way we represent power. Basically, all we've done here is change the way we've represented the power, isn't it? Do you know what I mean? Yeah. Because all I've said here is I've got 1 volt in, what's the voltage out? Okay, it's going to be 2 volts peak to peak. But we must understand that in a transformer is a passive device, isn't it? And that's really what we're talking about here. Because it's passive, no power is being added, so we know that the current at the output must be half the current at the input. Because VI is power input, isn't it? Must equal the VI output, apart from a little loss in the transformer itself. So, because of that, we can say that here, the gain of this there is no gain. The gain is 0, right? It's not 1, it's 0. Gain is 0. I'm going to come back to this gain of 0 in a minute. All right? No gain. Nothing has been added in terms of power. The only way you can add power is if you use an active component. An active component takes a DC power and changes it or adds that power to the signal. Now here, in a power amplifier, I could say, for example, let's say I have 1 watt input and 10 watts at the output. Power. Now this is power now, not voltage, not current. We don't know what the current and voltage is, that could be anything. We can actually use a transformer at the output to change the ratio to anything we want.
Again, 10 divided by 1.
Yes. Now here we can talk about gain as equaling power out over power in, can't we? As a ratio of the two. Here we're using the ratio, so therefore we would say in this case the gain is about 10, isn't it? Because we've got 10 times more power coming out of the device. Where does that extra power come from? How can I get more power out than I put in?
From the power amplifier.
Yeah, from the DC power supply to the amplifier, yes. See, we can't get something for nothing. That's where it actually is coming from. In other words, we must have here an active component of some description. Active meaning it's going to change that DC power into the signal power that we want. And that's when we talk about gain. So we cannot really talk about gain in a passive device. All we're doing here is changing the ratio of voltage to current. That's not an increase in power output. You should know. Okay, so we have an idea now about gain as ratio of power. And whenever we talk about gain, we should really be thinking of power ratios. Right. Okay. Now, once you understand that little point, and you've accepted that, now we're going to talk about logarithms. Okay, now we're going to talk particularly about logs to the base of 10. So let's talk about, first of all, indices. And let's take some examples. For instance, if I have 10 to the power 1, or 10 to the power 2, 10 to the power 3, etc., 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 what does this mean? For instance, what does 10 to the power 3 mean? No. Mathematically, what does it mean? Not the name given to it. What?
10 3 times.
Yes, 10, that's exactly it. Multiplied by itself 3 times.
Yes.
You know, not just the name. I know it means kilo if we put a name to it. But mathematically, it's 10 multiplied by itself 3 times, isn't it?
Yes.
Okay? So we could put that as 10 multiplied by 10 multiplied by 10. You know? And of course 10 to the power 2 is 10 just multiplied by 10, isn't it? 10 squared. What's 10 to the power 1?
10.
Yes, just 10 multiplied by nothing else, just 10. Okay, what about 10 to the power 0?
1.
Yes, you all remember that from your math days. In fact, anything to the power 0 is 1, isn't it? Whether it's 2 or 3 or 4, whatever it is 1 in that case. These are common logarithms to the base 10. You can take logarithms to any base you like, but in our case, when we talk about decimals, we're going to talk about common logarithms, logs to the base 10. Now, another way of presenting these indices is to do it the other way round. For example, if I said the logarithm, log, to the base 10, we normally write the 10 underneath here as a subscript. Log to the base 10 of, say, 1,000, the logarithm is the number you've got to raise 10 to get that number. So in this case it would be 3, wouldn't it? All right. It's a different way of writing it, but it's the way we've got to think about it. Logarithm to the base 100 is 2. Logarithm to the base 10 of 10 is 1. Agreed. And logarithm to the base 10 of 1, 0. Do you see how we've converted the two? Right. Okay. Now this, of course, is just revision work. You've done this before, so you know.
Just to write the power.
Basically, the logarithm of a number is the number you've got to raise 10 to the power of to get that number. We've got to raise 10 to the power 3 to get 1,000. We've got to raise 10 to the power 2 to get 100, 10 to the power 1 to get 10, and 10 to the power 0 to get 1. Okay? Quite straightforward so far. No problem. All right, now let's have a look at some other values. I'm going to just erase this now off this side of the board. Right, now it becomes a little more tricky. These are whole numbers, whole integers. All right, so the logarithm of 1,003, logarithm of 102, these are quite straightforward. Just count the number of zeros. How many times we're going to multiply 10 by itself. But what if I posed a question, what if I take the logarithm to the base 10 of a number less than 1? For example, 0.5.
Divided.
So now,
That's schedule.
yes. Now this is here we're dealing with positive numbers, okay, and these are whole numbers, aren't they? But what if I go to a number less than 1, such as 0.5? The logarithm of 0.5.
Multiply or
Above a number divided by another, 10 power of number divided by number.
Well, I'm not quite sure if I understand exactly your logic there, but all right, assuming we don't know the answer to this, what do you think it's going to be? Look what we're doing here. As the numbers go lower and lower and lower towards 1,
You get a negative result.
right, we've got to start talking now about negative numbers. Anything less than 1,
negative.
we're talking about a negative number. Okay? That's essentially the bottom line. We're talking about a negative number. Actually, if you took, I don't necessarily expect you to know this offhand, but it is something worth remembering because we're going to deal with this. If you take the logarithm of a number less than 1, you really have to use either a lookup table or log tables to find this out. Or if you've got a calculator, does anybody have a calculator with logs on? You don't have a calculator with logs on. Okay. Okay. Then you'd have to look at the number. So if I have a log of any number less than 1, doesn't matter what the number is, a fraction in other words, then the answer here is going to be a negative number. Okay?
There is no results for negative numbers.
Well, actually, it's just a negative log. You take the log and then it's
No, log negative 0.5 or log negative 0.5.
it actually the log of negative 0.5 is like saying, what we're saying here, let me put x here as an answer, because this could be any number, that could be any number. Then we say 10 to the power x is equal to 0.5. If I put a minus sign in front of that, it's just like having a minus sign in front of this. It doesn't alter the actual number, the log. Okay? But in fact, because this is a number less than 1, because this number is less than 1, this would be a minus number. X itself would be a negative number. So it's like 10 to the minus x.
1 divided by 10 to the minus x.
Yeah. 10 to the power x, or whatever it is equal to 0.5. And it's the same if we took fractions. For instance, let me choose an easier one.
No, I meant you can add this also in the way. It's equal to 1 divided by 10 to the power x.
Yes, it is. Yes, it is. That's right. Indeed. I'm going to come to that in a minute. In fact, we can even go even further than this. For instance, let's say I asked you this question. Log to the base 10 of, say, 0.1 is equal to 0.1.
Yes.
Now, that's a number less than 1, isn't it?
Yes, minus.
Yes. Now, the logarithm of 0.1 is a logarithm of a number less than 1. But we can also say it's the logarithm to the base 10 of 1 over 10, isn't it?
Yes.
So what do you think that answer is going to be? Well, what's the logarithm of 10? 1. So what do you think this one's going to be? Minus 1. Exactly. Minus 1. Remember,
occupy the same physical link. For example, a frequency band in a microwave system, or a coaxial cable, or an optical fiber. We have one physical medium, and we want n inputs to go across that. And by multiplexing them, we give each of them a portion of the capacity of this link, and that portion is called a channel. So we have one link with n channels. Then at the other end, we need to demultiplex. Take these channels of data and route them to the various outputs. That is the usual method of doing multiplexing, and it's true whether we're looking at any of the techniques that we're going to be talking about in this session. There's one variation that I think is worth mentioning, and that's what I'm calling internal demultiplexing, which is shown on this slide. Again, we have n inputs, and we're feeding them through a multiplexer onto a single link. But at the other end, those inputs are going into a computer, and it is often the case that the computer will understand the channel structure that is being used here. So you don't need a separate box here known as a demultiplexer. Rather, you take this line right into the computer in a single physical port, and then there is logic in the computer that knows what multiplexing scheme was used, and therefore can do the demultiplexing. So that's a slight variation, but the same principle is involved. So now let's look at the techniques that we're going to be discussing throughout this session. And as I mentioned, there are 3 of them. There's frequency division multiplexing, synchronous time division multiplexing, and statistical time division multiplexing. The latter 2 are both forms of time division multiplexing. And before proceeding into the details, let's look in general what the basic distinction is between FDM and TDM. And that is shown here. With frequency division multiplexing, we take the sources of data through a multiplexer and assign them to a frequency band, so that each of the channels is a band of frequencies on the same physical length. Then for demultiplexing, these frequency channels are routed to various outputs. So simultaneously, all of these transmissions are occurring, but they're occurring at different frequencies. By contrast, with time division multiplexing, we're only going to send information one at a time. Only one device will be transmitting at a time, or to put it more correctly, data from only one device will be sent over this multiplex line at a time. So what we do is we assign time slots, and during time slot 1, we take data from source 1, time slot 2, source 2, and so forth. And then at the end, after all these, in this example, 6 stations have been given a time slot, we start over again and have a new round of time slots. At the other end, as the data comes in, each time slot is routed to the appropriate output. Now, in terms of frequency division multiplexing, we're saying that each of these frequency bands is a channel. In time division multiplexing, a channel consists of the sequence of time slots assigned to a particular entity. So this time slot 1 and this and so on, that sequence of time slots devoted to source 1 is called a channel. And from the point of view of source 1, in fact, it is getting a channel. It really won't know whether we're using time division or frequency division multiplexing. Okay, now let's turn and look specifically at frequency division multiplexing. We'll start out with a slide that by now should be familiar to you, which is our old friend doing full duplex transmission on a voice grade line. We've talked about this before, that we're going to use FSK, and we will transmit in one direction using one pair of frequencies, and another direction using another pair of frequencies, and that the spectrum that results is shown here. So what we're doing now is we're simultaneously carrying two data channels on the same link using different frequency bands. Now in this case, we are sending them in opposite directions. Typically when we talk about multiplexing for line sharing, we're talking about sending things in the same direction. But the concept is the same, that each signal has to have its own bandwidth that is separated from the bandwidths of the other signals. Let's look at another example and go back to the example of a TV signal that we mentioned in one of the early sessions. As we talked, a TV signal typically is about 4 or 5 megahertz in bandwidth to construct the entire signal. And the example we showed, we saw that this bandwidth was from 0 up to about 4 or 5 megahertz. That was the portion of the spectrum used by a TV signal. Now, if we're going to multiplex TV signals, we would like to use more than one of these 5 or 6 megahertz bandwidths and spread them out across the spectrum. And this slide shows how to do that. Do it by using amplitude modulation. This envelope here, if you recall from a previous slide, is a pattern of a few lines of video transmission. We have here the horizontal blanking pulse with a sync pulse imposed upon it, and this is used for the horizontal retrace. And then there is a scan of the line with the height of this line, the amplitude of this line corresponding to the relative brightness or darkness of the picture. So you have a sequence of pulses separated by these lines for scanning. Now, if you recall also, when we talked about amplitude modulation, you take some carrier signal and you modulate the amplitude of that carrier signal according to the signal that you want to transmit. And the result is this kind of a wave pattern. The sine wave that is shown in here is the wave that we are actually transmitting when we do amplitude modulation of a TV signal. So with that in mind, we can then look at what the bandwidth pattern of a TV signal looks like. And that's shown on this slide. We have here a video carrier, which we'll call F sub CV, and this is the carrier that was shown in the previous slide. It's that constant high-frequency sine wave upon which we impose the video signal. And if you recall when we talked about amplitude modulation, there are two side bands that are created with amplitude modulation. The spectrum is reproduced to the high end and to the low end of the carrier signal. And what's normally done in a video signal is to reproduce entirely the upper side band and to reproduce a little over 1 megahertz of the lower side band. This improves the fidelity of the system. And the result is that this spreads out over between 5 and 6 megahertz. This is the bandwidth of the video signal. At the same time, we're going to add a couple of other components, a color subcarrier, which in the case of color TV, this will contain the color information. This is a very narrow bandwidth signal, and by putting it way up here, it really won't interfere with the quality of the video signal. And then finally, at the end, we tack on an audio carrier, which only needs a few kilohertz of bandwidth to be represented. So this entire thing can be fit into 6 megahertz. And this 6 megahertz is a bandwidth. Where it specifically occurs along the spectrum depends upon this video carrier. It can be a very low or a very high frequency. And the result is that it is possible to put a number of video signals onto the transmission channel. And in fact, standard I'm sorry, onto the same transmission link. And in fact, standard channels have been defined for video. And these are shown here for VHF. If you recall, VHF is one of the bands for transmitting signals. And what is shown here is, in terms of megahertz, the bandwidth of the various TV channels that can be broadcast TV channels that you can get in your home over a TV set. And as you can see, each of these channels, for example, channel 5, is from 76 to 82 megahertz. Each channel occupies a 6 megahertz bandwidth, but we've put the channels on different portions of the spectrum, and they don't overlap. They're adjacent to each other in these two chunks, and they don't overlap. So this is a very good example of frequency division multiplexing. This can be transmitted over a microwave terrestrial system, a satellite microwave system, or very commonly coaxial cable. And what you've done is you have one physical link and you have multiple signals at different frequency bands, and you've achieved frequency division multiplexing. And I should point out, frequency division multiplexing requires the use of analog signaling. Recall again, back in an earlier session, we distinguished between analog and digital signals, analog and digital data. We can use FDM on either analog or digital data, but we first must encode that data onto an analog signal. Once we've done that, we must then modulate that signal up to a particular frequency band, and then we can share a physical cable among a number of channels. So what we've talked about so far is the use of audio data for, the use of analog data to do this kind of multiplexing. Let's look at it in a little more general terms now. Here is the transmission using frequency division multiplexing. And what has to be done is a conversion of the data to an analog form at a particular frequency. And in this case, we call these carriers. We've used the word carrier to talk about modulation onto an analog signal. We'll call these subcarriers because each one is providing the use of a subset of the total capacity. So we'll talk about having capital N, input signals, each of which will be modulated by a carrier frequency. And as we've seen, there are two forms of modulation. If it's digital data, then you'll get out an analog signal using, for example, amplitude shift keying or phase shift keying or frequency shift keying. If it's analog data, you use amplitude modulation or phase modulation or frequency modulation. Regardless of the modulation technique that you use, what you end up doing is creating an analog signal that has a particular spectrum, has a particular bandwidth at a particular point on the spectrum. And you do it in such a way that these carriers are distinct and that the bandwidths that are produced don't overlap. Then you can sum them all together to produce a composite signal for transmission. And it's sometimes the case that you'll do a further level of modulation if, for example, you're going to be doing modulation in stages, which we will see in a few moments. Then you might do a further level of modulation to finally get the signal that will be transmitted. But the minimum essential is up to this point, that you have done the modulation and then you have summed the components. So this is transmission. Let's now look at what the signal will appear as it is being transmitted. That is shown here, where we show the signal for a frequency division multiplexed line. We're talking now about the composite signal that was on the previous page, and what you see is that there are bandwidths centered at these various carrier frequencies or subcarrier frequencies. And hopefully we've designed it so that the spectrum, they do not overlap a spectrum. And consequently, we have preserved the integrity of each of these signals as they are transmitted, and they're all transmitted simultaneously. Each of those frequency bands then is known as a data channel, or simply channel. Okay, that's transmission and what the signal looks on the line. Let's see what happens at the other end where the reception takes place. Again, we're talking about a signal coming in, and if we use that terminology, S of t, which was modulated up to a particular frequency after we had the entire composite signal, we may have to do this step of demodulation. Then the entire composite signal, which has all of those frequency components, is simultaneously passed through a number of filters. And each filter, the point of each filter is to just capture the particular bandwidth around a particular subcarrier. So the first data channel will be filtered out and captured by this filter, the second channel by this filter, on down to the final channel. Then the signal that's coming out here should look very much like the analog signal that was initially produced, and we have to demodulate it using the carrier frequency again to get back the original signal that was sent by the input device. So we finally have reached the point where we're back out to the original signals that were sent in. Over the line, they were a composite signal, and we have split them out by filters, and then we've recovered the information by demodulation. Let's look at a specific example of this frequency division multiplexing, and want to look at voice signals. Talked about the bandwidth of a voice signal being approximately 4 kilohertz, or at least it can be conveniently contained within 4 kilohertz. So, typical voice signal that would go out over the twisted pair telephone wire coming out of your telephone line would occupy a spectrum from 0 to 4,000 hertz and have roughly this kind of shape. Now, if we were to modulate that signal, this is an example of an analog data being modulated onto an analog signal, we would end up with an 8 kilohertz signal centered at the carrier frequency and having 2 sidebands. What's typically done with voice signals is to take just the upper sideband, to delete the carrier and the lower sideband, and to send out the data in this fashion, so that multiple signals from various sources can be modulated by particular carriers and share the same line. And so in this fashion, you can get, depending on the bandwidth of the line, you can get whatever that bandwidth is divided by 4,000 kilohertz, and that tells you how many voice channels can be simultaneously carried. Now, standards have actually been created for this. There is a convention that is used. It was initially set up by AT&T, but it is also used by the other private carriers. And there's a similar standard used in Japan and Europe and the rest of the world. But these are standards for setting what frequency bands to be used for multiplexing these voice signals, and what groups or chunks of signals can be carried. And North American standards, which were developed by AT&T, are shown here. And all they've done is they've designated groups of channels with a particular name. And for example, a group will be 12 channels, and 12 voice channels times 4,000 kilohertz is a total bandwidth of 48 kilohertz. And the spectrum that it's defined to occupy is here. So what is done, and you'll notice that in most cases these spectra don't overlap. If you want to send data over a relatively low capacity line, like a twisted pair line, you would multiplex either at a group or supergroup level and send those phone or voice signals out over the line. If later on that twisted pair line feeds into a coaxial cable transmitter, you can add that group to other groupings and get more voice channels on the same physical link. So the point of these standards is just so that it is easier to make the intermediate equipment where the multiplexing and the demultiplexing takes place. And they're just standard groups of channels that are used. Also, because they're standardized, their rates can be set, and it's possible to lease a particular capacity. You can lease a 12-channel capacity or a 48-channel capacity or a 500-channel capacity and so forth. So the thing is standardized both from the point of view of allowing equipment to be built that is used in a variety of places, and also so that standard rates can be set. And one other aspect of that we can look at in this slide is how that is actually implemented in the AT&T long-distance system. And they define what they call a hierarchy. And what they do is they define the multiplexers that will be used to multiplex voice signals into higher and higher groups. So, for example, at a group level, we're taking 12 voice signals and multiplexing each voice signal on a particular carrier frequency to produce a composite group signal. That group signal can then be an input into what's known as a supergroup multiplexer, which will take 5 groups of 12 signals and produce a composite 60-channel output. And by standardizing in this fashion, these multiplexer units can be manufactured in large quantities by AT&T suppliers. And this goes up to higher and higher bandwidths to correspond to the various transmission media such as coax and fiber and satellite that are used. And again, by standardizing this, they can mass produce the equipment and they can also set particular rates. So that in essence is the technique of frequency division multiplexing. Key points to remember is that analog signaling is required and that bandwidth separation is the technique used, and signals are transmitted simultaneously along a number of channels. I want to now look at time division multiplexing, which in contrast uses a time slot technique. And it assumes that we're dealing with digital data rather than analog data, because we want to separate in time. With digital data, you can put so many bits in each time slot. So whether or not we're using an analog signal or a digital signal,